Hello, and thank you for joining us for the Consulting Specifying Engineer webcast, Arc Flash Mitigation Design, brought to you by ABB, ASCO Power Technologies, and Meltrick. I'm Amara Rozgas with Consulting Specifying Engineer and CFE Media and Technology, and I'll be your moderator today. Let's learn about this platform. If you're having trouble with your slides or with the audio, please refresh your own personal browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, click on the question mark at the top right corner of your screen to do some system checks before contacting an online technician. If you do need a technician, type a message into the Ask a Question box and we'll get to you as quickly as possible. Answers will appear in the Answered Questions box. To download the presentation slides, use the Event Resources tab on the left side of your screen. Type questions for today's presenters in the Ask a Question box on the left side of your screen. You may ask questions at any time, and the interactive Q&A will start in about 45 minutes. If you're interested in learning for this particular presentation and earning a 1 AIA CES approved learning unit and health, safety, and welfare unit, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab at the top of your screen. The quiz will open in a new browser window, so I suggest you open it right now because that window will break off when this webcast ends. In keeping with the American Institute of Architects Continuing Education Systems Policy, please take a moment to read the quality assurance slide. All right, so here are the learning objectives for today's event, and we'll talk about these in today's presentation. Please note that any red underlined text you see is a hyperlink in the PDF where you can get more information. Now let's hear from today's sponsors. At the conclusion of the commercials, please note that any red underlined text you see, please note that there will be a moment to make up for varied internet speeds. Now let's hear from our sponsors.
We know that safety is always a top priority. Are you keeping up with the innovations helping to make safer power distribution possible? From the largest piece of arc-resistant switchgear to the smallest arc fault and ground fault sensing circuit breaker, ABB is designing ways to help lower the risk of harm to both people and equipment. A forgotten tool inside the enclosure is a common cause of arc flash. Reduce the risk of a tool coming in contact with the bus stack or breaker connections with ABB's IP20 certified bus stack. Help enhance operator safety with groundbreaking T-Max XT circuit breakers. Remote metering and monitoring allow users to access information anytime, anywhere. With support for over 10 communication protocols, you'll always be connected to what's happening in your power distribution system. Optional Bluetooth connectivity allows personnel to set parameters and check measurements directly from their smartphone, all from an arc-free zone. Accessories like reduced energy let-through modules help to further enhance operator safety. And surge protection devices and advanced voltage and frequency protections can help prevent power quality issues from damaging sensitive equipment as well. Work safer and protect your assets with innovative design.
Meltrick's switch-rated plugs and receptacles combine the functionality of a switch with the convenience of a plug and receptacle. As an approved line-of-sight disconnect, they provide a cost-effective means of meeting code requirements without the need for expensive interlocks or auxiliary safety switches. They ensure arc flash protection. The plug cannot be removed from the receptacle until after the contacts are de-energized. The receptacle's interior features a spring-loaded ejection mechanism that ensures a quick break of the contact and minimizes arcing. Arcing that does occur is isolated in enclosed chambers. Meltrix switch-rated plugs and receptacles are available in a variety of configurations, with ratings up to 200 amps, 600 volts, 100 horsepower, and Type 4X water tightness. For more product information, please consult your Meltric catalog or contact your local sales representative.
Thank you for supporting today's event. And now let's hear about our two amazing speakers. Zia Salami is a senior member of IEEE and is a subject matter expert in electrical power systems at CDM Smith. Zia has more than 21 years of industry and academic experience in electrical power systems and has served in several roles as an advisory engineer, consultant, and academic professor. Zia is currently working at CDM Smith as a management specialist, subject matter expert, electrical power systems to guide the company in design, modeling, and analysis and support to help resolve clients' technical issues. Ken Katsmita holds the role of engineering manager for the mission critical sector at Jacobs. Over more than 20 years, he has built a catalog of more than 700,000 square feet of completed data center and commissioning work for numerous commercial, federal, and municipal clients. He's responsible for the engineering, designing, and commissioning of power distribution systems for mission-critical facilities. He was the 2010 Consulting Specifying Engineer 40 Under 40 Award winner, and he's a member of the Editorial Advisory Board. I'm excited to get started on this discussion. Let's get going, Ken.
Thanks, Amara. So first, I want to talk a little bit about what is an arc flash. So NFPA 70 defines an arc flash as a dangerous condition associated with the possible release of energy caused by an electrical arc. An electrical arc occurs when the electrical current diverges from its intended path, say along a feeder or a busway, travels through the air from phase to phase, from one conductor to another, or to ground. Now, the arc flash can generate a large amount of heat, and this can exceed, 3,600 degrees or 36,000 degrees. Sorry. In addition to the heat of the arc flash, it can also create an explosion blast. And basically, what happens is during an arc fault, the high temperature vaporizes the electrical conductor, changing it from a solid state to a gas, and that causes it to expand outwards, which causes that explosion. So today, this presentation, we're kind of going to go through those hazards and then look at ways to mitigate or reduce those hazards. So why do we need mitigation? Well, when you look at it, it's really to protect lives. That a large amount of the heat can severely burn human skin, it can set clothes on fire, and that makes it extremely dangerous and potential lethal to human life. Another issue is the protection, then the reason we do it is protection of property. That explosive force that caused by the arc flash can do damage to equipment. It can do damage to the building. It can set fires. In addition, it could also injure humans working around the equipment or even bystanders standing by. So it's just protection of property and protection of people. And the third reason really is, protect client uptime. So once you have a fault, that facility can be damaged, and it may require the facility or the equipment to be shut down. So you're going to stop whatever functions happening, whatever production's happening. So it can cost them, a lot of uptime while it's happening. So some of the codes that you want to, some of the codes that are associated with arc flash, NFP 70 is the National Electric Code. Article 240.87 basically says that arc flash reduction is required on any overcurrent device rated 1200 amps or higher. And they provide acceptable means for reducing that arc flash, such as zone interlocking, differential relaying, reduce maintenance switch, instantaneous trip settings, overrides, and then anything that's proof equivalent means. And we're going to go through a lot of those today in today's presentation. The next two standards that the industry uses for their guidelines and analysis regarding arc flash and arc flash studies, the first one is NFP 70E. It's the standard for electrical safety in the workplace. This standard basically defines the guidelines for working on or around energized equipment. It also assigns that responsibility for the arc flash safety of the employees or employees. The second one is IEEE 1584. It's the IEEE guide for performing arc flash hazard calculations. And this standard really defines how arc flash calculations are performed. It defines the parameters used to determine the incident energy and the severity of the arc flash injury. Some of those parameters include the magnitude of the arcing current, the working distance from that arc flash, and then the duration that arc flash is allowed to propagate. So when you look at, general techniques for mitigation, the overall safety employee is really the top priority in any of these mitigation approaches. And ideally, the safest and most widely recommended practice is to not work on the equipment live, work on it in a de-energized state. Basically eliminate any of that potential for an arc flash to happen by de-energizing the equipment. To do this, it's usually set up operational maintenance procedures that can be developed to shut down the equipment before any work is performed, things like lockout, tagout procedures. You can also add key interlocks that can prevent opening equipment while it's energized. You see this a lot on medium voltage transformers where the upstream and downstream breakers will have key interlocks. Once you get the key, once those two breakers upstream and downstream are open, you take the key and it allows you to gain access to that piece of equipment. So it has to be de-energized before you can actually work in it. But sometimes this just isn't possible. For example, a lot of mission critical facilities, they're 24/7. They can't be shut down for maintenance. They really don't have any downtime. So that's where working on things alive is what we're going to kind of talk about more, is how do you mitigate those and make them safer. So one of the approaches is really remote operation or remote work. So basically trying to increase the distance between the person working on the equipment and the fault that actually happens. So you want to look at using remote operators such as a hardwired control switch, maybe a PLC-based human machine interface or an HMI screen. You can look at the SCADA systems that allow, and this all really allows the worker to be completely outside of the room or outside the arc flash barrier when that breaker or switch is operated. Other things are such as portable devices can be used, and it's basically where it's a remote racking or a portable device that can actually trip the breaker remotely. It's more portable. It's kind of a wired device. There's also remote racking, which allows you to withdraw that breaker, make that separation from the bus from a safe different distance. Some things to note is, these things all add cost to the project, so you just have to be aware of those. So when you can't work on a piece of equipment de-energized or remotely, that's just not possible. It requires personal protective equipment, PPE, to be worn. So you want to be able to wear PPE to protect yourself. And basically PPE is the clothing and equipment designed to protect the wearer's body from injury by reducing the worker's exposure to that incident energy. So the rating and the type of PPE worn is based on the calculated exposure exposure to the incident energy. So that's what the arc flash calculation is for. It kind of tells you what that incident energy level is, and then you can provide the proper PE to work on that equipment. Now, NFP70 does provide guidance on the selection of that arc rated equipment and other PPE based equipment based on the exposure. PPE can include stuff like safety glasses, hearing protection, hard hat, arc rated gloves, arc rated flash suits, and then arc rated suit hoods that go over to protect your face. Now, the big thing about arc mitigation and arc flash mitigation is really knowing and understanding the potential risk. That's where arc flash labeling comes in. It kind of tells you what the incident energy is, and you just have to really understand what that means. So training of personnel on the arc flash label, on arc flash, training them on how to properly use PPE is very important in the mitigation of the hazard, just really understanding what that hazard is and how to protect yourself from it. So with that, I am going to turn it over to Zia, who's kind of going to help explain how we anticipate that risk and go over some of the mitigation techniques.
Thanks, Ken. One of the powerful way or to detect high incident energy and also anticipated what type of energy we will get during the design condition or even during the coordination study is new concept referred to C area plots or standby energy area plots. This is new concept by ETAP, and they have implemented in their software. Having said that, this is for radial system at this point and not for the loop. They're planning to continue this concept in the near future. Analyze an ability to evaluate risk considering many variation as design input and present a set of event for each equipment with the single plot. We'll see that one in the next slide. Let's have a one-line diagram. There are two feeders coming to the facility, and they're feeding the 4 kV system and 480. And we're trying to analyze what's going to happen on the MCC1 with respect with the C area plots and define that concept. Remember, C area plots is a concept, constant energy plots. Let's look at this TCC and let's look at the design that we have for MCC. If there is an arc at MCC level, and we're trying to make that one as a 8 calorie per centimeter square. Therefore, if we plan to do that, we can utilize the C area plot or constant energy plot to determine during the design phase, as I mentioned, or during the coordination study phase, if that design will hold, including all the parameters, design input parameters that require to perform arc flash calculation, such as the minimum and maximum short circuit, voltage variation, electrode configuration, conductor gap, enclosure size, and working distance. Therefore, this area plot concept, considering all the parameters that can resolve with the constant energy plot as a design or as a reference. In this case, let's talk about 8 for our design. Now, we also have a circuit breaker settings currently. Let's say the short time band is 0.33 seconds, and the instantaneous setting is disabled. And this is a new design. We were starting with that new settings, and we want to see if we can achieve at any condition 8 calorie per centimeter square at our MCC1. As you see here, before the intention is that protection or protected device has to be below the brown box, which representing the area plots or energy, constant energy. Therefore, if we're able to achieve that, that is guaranteed at any time or any point that we will get under any design input, we will achieve 8 calorie per centimeter square. Therefore, before we continue our discussion, let's look at how we're able to create this area or this curve referred as a C plot, utilizing the TCC reflecting into TCC. We have here a short clip that define how you put the information into a tab and how the C plot will be created. Then we'll continue our discussion after you see this short clip. Thank you. Let's look at the MCC1 for the C area plot. At this point, we go to bus editor in eTab. Under that, under Arc Flash tab, we can see it says TCC plot energy, C line or C area. The focus today is on C area, and let's look at the bus side and selecting the setting variation for bus side. We go to the settings, and as you see here, it says design level and location. We can put any design that we have as a constant instant energy. We can select 8 for now. And we have choices of the location, bus, line side, or load side. Let's stay with the bus side as just for presentation. We have voltage variation, tolerance. You can put any variation that you want. Short circuit, symmetrical current, 3-phase bolted fault current, variation, mean and max. We can consider the arc current or not. Electrode configuration, you can select vertical or horizontal or both, depend on your configuration. And then we have a gap variation, upper limit and lower limit. Then we get to enclosure dimension that we have height, width, depth, the same upper limit and lower limit. You can have any variation percent enter into this box, and then working distance. After you populating this information as a parameters, you can look into the C area plot and evaluate the area that concern. Here, what we have as we presented here. As you notice that how we able to create that C plot within the TCC. Now let's going back to our design. Now, for previous setting, the short time band, we realized that we cannot achieve that 8 calorie per centimeter square constant, because we had overlapping with protected device, or some areas, some of the region was below our protection. Now let's move that one, the time short time band, make it shorter, make it higher from 0.33 to 0.18 seconds. See how that improve our design. As you see here, design is much better, but it's still we have possibility to fail, especially the area that we are overlapping with brown box or the C area. But I can tell you that probably we will get not much more than a bit more than 8, but it's still, if we just clearly we're going for 8 as our design, this will not gonna be, still we are short on that. Having said that, this is might be a bit more, but for people want to take it or accept that as just their design, that is fine. But for just the training and presentation purposes, let's move on to make it more based on what we designed to plan to do that. As you see here, our design is passing mainly because now we are enable the instantaneous portion of the circuit breaker, and now our protection, complete protection and settings are below the area or C area or constant energy. That tells us that at any time, with all the variation that we are involved with performing the arc flash, those variation that I already pointed out, we are guaranteed that we will be below 8. Actually, in this case, probably much more than below 8 in some cases, and therefore that will be eliminating a lot of runs because we just have, based on what we did, based on these settings, and this is guarantee, again, based on the minimum and maximum short circuit, available short circuit at the facility, based on voltage tolerance, and based on other tolerances, as you saw in the clip, that is part of the arc flash study. Now, the only issue that we may have that we may have miscoordination, or some coordination difficulty and challenge with downstream devices. Let's go to next slide. Now, we're planning to change our design from 8 to 12. Let's make it, I mean, it's kind of sacrificing between either the coordination, arc flash, instant energy calculation. It's always been challenging actually between the calculating the arc flash and instant energy, and also coordination is just kind of the balance. Of course, we always go for the safety, but this is a challenge. It's been for our everyone between these two type of study. Now, for here, we change the design to 12. We're going back to our original short time band. We disable the instantaneous. That give us more chance for having coordination with downstream devices. And well, here in this case, we're still passing, but we had to sacrifice 8 calorie constant with 12, and therefore is kind of the trade-off. But this is guarantee again that at any condition we will get 12 calorie per centimeter square if there is a arc at this MCC, at the bus, and so. Anyway, that was just a kind of big picture, and this new concept, CSE concept by ETAP. I was going to bring it to your attention again, that can be used during the design phase or coordination phase, and eliminating many runs and guarantee what you're looking for. Let's move on to another mitigation approach, which we typically we always pretty much rely on that, and I'm sure most of us have done that, changing the existing protected device type or settings. Again, that's always, to me, one of the probably easier or cheapest approach. Of course, we need to make sure the intention to bring the fault clearing time, FCT, lower. Consequently, by bringing the FCT lower, you're improving your instant energy total. But of course, we have the, again, challenge with the coordination issues that we have to deal with, how much we can bring the settings or instantaneous down and not having the issue with downstream devices. But this is that approach that can be done, either changing the settings or changing the type of breaker that has more flexibility of the adjustment. All right, let's look at going back to our one line that we start. We are going to use utilizing this one line for our discussion, our presentation. Ken and I going to use this one line for going through, show you a few sample and simulation. Therefore, going back to our system, what we had, 2 feeder feeding to facility, 13.8 to 4 kV system, then going back to 480 volts, and there are some loads connected. Now, let's look into what we want on this one here. Let's just look at emphasize on the switchgear A. Switchgear A has a relay, upstream relay, that protecting not only the cable and protecting the continuous amps of the switchgear, and of course has to be protected or coordinated with the fuse downstream. Now, going back to the one line, in this case, my relay again set to time dial 3, and I'm coordinating my downstream fuse, which is fine. But when I see that and doing the arc flash calculation, I notice that I have now IE around 7.5, and with the FCT 0.75 seconds, and the boundary, arc flash boundary, around 9.6 feet. But realizing that I had more space, that bring my relay down. remember that the lower fault clearing time, that causes lower arc flash because we are holding the energy less amount of the time when the releases, therefore it will be less. Now, in this TCC, we change from the time dial, the relay, we brought it down to around 1.14. And now, as you see here, it's still coordinating the fuse that I have. What I had to do, change the fuse also, and move the fuse to the right with the smaller ampere, but it's still protecting my transformer between the min and maximum short circuit. And now let's look at the arc flash. Now I have almost half IE and send energy because the fault FCT came to around 0.336, which almost half, and that would be reducing the arc. Therefore, keep eyes on this changing as one of, probably I'm suggesting your first or second option, which going to be much cheaper. Now, at this point, I give it back to Ken to continue the current limiting and fast acting fuse.
Thanks, Zia. Yeah, I agree. I think, the first step is to look at your arc, flash study, see what you can do, adjust the ratings. I know I did a lot of studies with mission critical facilities where they tend to set everything as high as it can so that you don't have any trips. And when you went in there, that really affected the arc flash. So you had to really go through and try to adjust those settings. So that is a very good approach. The next one we want to look at is current limiting fuses. So basically a current limiting fuse limits that short circuit pass-through current, which will then lower the magnitude of the arc. There's also fast acting fuses, which is basically just gets rid of the delay. There's no delay in the protection, which will shorten that time duration of the arc. So both of those are used to either reduce the magnitude or limit the arc duration, which will help with the arc flash or the incident energy level. One thing you must be aware of is that these fuses can oftentimes be very difficult to coordinate. So when you're doing a coordination study, just make sure when you use these type of fuses to look at how it affects with the breakers upstream and downstream of them. The next one is arc resistant switchgear or arc resistant equipment. And it's really designed to provide protection to the workers or the work surrounding the equipment from internal faults. So this type of equipment doesn't really reduce the energy stored in the circuit, but what it's designed to is to withstand the effect of the fault. Basically, keep the fault within the gear and then redirect that energy away from the operator. If you look at the picture, this is a picture of an arc flash resistant switch gear. It's 15 kV gear. You can see that the joints, it's a very sturdy, steel construction. The hinges are very sturdy. They're robust. You can see there's multiple hinges to keep that door on. The doors are bolted shut to prevent that door from flying off during an arc flash event. And then as you can see in the top, there is a duct that basically takes, so there's arc chutes within the gear that take the arc explosion and that energy, funnel it up into the ducts on top of the gear and then out the back of the gear where there is a concrete block room with louvers to the outside. So it's basically takes that energy and redirects it away from the operator. And again, so because this is not really a reduction, you can't really simulate it in the arc flash studies that Zia was talking about. You really have to calculate the incident energy level and what's being released and then compare it to the rating of the equipment. What is that equipment rated to withstand? And these ratings are really based on the doors being closed. So once you open the doors, that redirection or that pathway disappears and allows it to come out the front. So this is really meant for operating breakers and things like that. One thing to be aware of, these are because of the robustness, because of the ductway and the redirection of air, the location of these, how they get vented. There's the space constraints because they're just larger. And a lot of times they require cable entrances from the bottom because of that vent ductway on the top. And there's different kind of gear, so there's different kind of ways that they redirect that air, but it's something to be aware of. Another approach is infrared viewing windows. And this is really to allow that operator to scan cable connections and components on live equipment, so they don't have to remove the covers and then do that scanning to make sure things are loose. And part of this is to the PM and the preventative maintenance to prevent arc flashes from happening. And part of that is to make sure that your cable connections are tight, that there's no loose connections that can create that arc flash. So this is one of those ways to do a preventative maintenance, but do it in a safe means by using the infrared windows to allow you to do that thermal scanning. And again, you can have these on medium voltage equipment. You can have them on low voltage equipment. It's really set up to look at the cable connection points and also some of the bus connection points. Another approach is basically a maintenance mode switch. And basically what this does is allows you to have more sensitive instantaneous settings. So basically you would go up, if you have your normal settings for the normal operation, you have good coordination between the up and downstream, but because you had to push the instantaneous or the short time up a little bit, it extended the duration, which caused a higher arc flash rate or a higher incident energy. So what this does is if you're going to maintain that piece of switchgear, you could go into the breaker and adjust it to a maintenance mode, which then takes those instantaneous short time settings down to a low level, which will allow it to clear the fault much quicker. So it eliminates all the time delays in that breaker. And it basically allows you to maintain coordination under normal operation, but lower it and be safer under a maintenance condition. Now, there's depending on the manufacturers, they have different means to do it. Some do it right in the trip unit where you have to go in and adjust the trip unit. A lot of people don't like to adjust the trip unit once it's set. So in this picture here, there's actually a switch above the breaker. Different manufacturers have a separate switch. It's all labeled maintenance mode. This one in particular was a client that didn't want these to be left in that mode. So when you put it in that mode, a blue light shines, so if they quickly look into the gear, they see blue lights, they know somebody left it in maintenance mode. They can go set it back to normal. And they do have these available for both low voltage and medium voltage systems. The next approach is the optical light detection relay. And this relay uses light sensors to detect the fault or the flash of light associated with the fault. And then it uses the combination with a relay that detects the high rise of current. So basically when you have both of these conditions, you have the fault, you have the flash, you have a high rise of current. The relay will clear the fault by operating the upstream breaker immediately without any delay. So it's basically once it detects the fault and it detects the high rise, it opens the breaker within 1 to 5 milliseconds, basically extinguishes the arc, doesn't allow that duration, which increases the incident energy. And for the protection, this is kind of why it's a two-part relay. It's a combination relay. So you have to have both conditions present to trip that breaker. So a burst of light, like if you take a picture, will not cause it, or a high inrush current due to inrush alone will not cause it. You have to have both the light flash and the high rise of current from the fault draw to trip that breaker. And if you see that picture, there's a picture of the optic light sensor in the backside of the 15 kV gear. And basically that just gets looped into each cable section. So if there's a fault anywhere in that board, it will trigger that main breaker to open up. So for this one, I know there's some questions of how do you simulate some of these techniques in SKM or ETAP. And for this case, in the picture, it shows the 4160 gear. Under normal conditions, it's about an 8 cal or incident energy level, or 8,000 cal incident, or 8 cal, incident energy level. Basically, for this scenario, what you do is you set the fault clearing time. You manually set the fault clearing time to match that light sensor, which in this case is the 0.01 seconds. So really quick clearing time. And you can see that because of the clearing time, the duration is low, and that brings the incident energy down to, below 1. So it becomes a safe zero category PPE type. Well, there is no zero category, but a low non-PPE required type equipment. So that's how you would adjust that. With that, I'm going to turn it back over to Zia to talk about the last in zone interlocking.
Thanks, Ken. Let's talk about, this is our last mitigation approach for our presentation today. Zone selective interlock. The advantage of this approach, which can be not only bringing the energy lower, also that would be able to help us on the coordination with downstream devices. Typically for LV system and in general, let's look at going back to our model one line. And if you remember, we were working on the MCC1, which is right here. And in normal condition, let's say we are coordinating these two with no ZSI, no zone selective interlock. And again, that's the rule of thumb that you have to coordinate incoming breaker with the feeder breaker. That's fine so far, but let's look at the coordination as far as the arc flash concerned, instant energy calculation. With this system, when the incoming circuit breaker to 480 volt MCC, and would be calculating if there is an arc on that one, we get about 15 something cal per centimeter square, with the FCT about 0.33 seconds, and boundary 7.5 feet. Now, are we able to reduce it? Let's try the ZSI. For the next picture, including the ZSI, as you see here, now we're able to reduce it with around 2.3 cal and 0.05 second FCT, and considering the interlocking between the incoming breaker and the feeder breaker to feeder ones, CB1, to be able to achieve that. Now, I think by next slide, maybe we will see it a bit better right now, that we able to enable the instantaneous portion of the incoming breaker. That's why it helps us to bring the instant energy lower at the MCC level. But in the same time, we can have a coordination with the downstream breaker, because downstream breaker feeder CB1 can prevent or delay the incoming circuit breaker from tripping on instantaneous part by the time delay that we assign. Let's say in this case, next slide, we assign 250 milliseconds time delay, that if there is a fault on the feeder terminal, that feeder, there is a fault. Therefore, based on what the delay that we had, keep in mind that our incoming circuit breaker instantaneous is enabled, but if there is a fault at the terminal of that feeder, as you see here, this is the sequence of operation. Still, my feeder breaker will go down first, then my incoming breaker, and then, of course, on the primary protection, which that's the right sequence of event. And mainly, again, that shows that there is a coordination, because we preventing or delaying the incoming breaker if there is a fault. The ZSI probably would be one of our, can be one of the top probably choices, but it required, of course, cable control and hard wiring, maybe just a little costly than changing in the process. But again, I think that would be one of the good approach for mitigation strategy if we can implement it in our facility. All right, that's all we have for today. At this point, I will hope this presentation help you. At this point, I will pass it to Amara for the rest of the presentation.
Excellent. Well, thank you, Zia, and thank you, Ken. That is a lot of information to take in. And let's take some questions. Please type your question into the Ask a Question box, and please type the presenter's name before the question so I know who to ask. We will get to as many questions as time allows, and questions that we do not get to will be posted at www.CSE210916.com. To download a PDF copy of the slides, please use the Event Resources tab. And of course, you can take the exam to earn your Learning Unit certificate. That exam is also available in the Learning Unit Exam tab. That link will break when this webcast ends, so I suggest that you open it now. All right, so let's get to a couple questions. Let's see here. We have quite a few. And Zia, I'm going to send this first question over to you. Let's talk about the frequency of arc flash studies. How often should you do one?
Yeah, good question, and we all need to know. Based on the NFPA 70E, the frequency is 5 years, or if there is a major changes in your system, because if there are some modification within the facility, and for example, if they change the utility feeder to their facility, if they change a large pump or pretty much the contribution system they add in the panel or reroute the cable, that would changing the behavior of the facility or behavior of the system and is not going to be the same. Therefore, they need to perform the arc flash study. Short answer to your question, 5 years, or if any changes in the existing system.
Got it. Thank you. All right, Ken, this next question is for you. This is a code question. Is NFPA 70E enforceable, and is it really considered a code?
So NFPA 70 is really an industry standard, so it's not enforceable. OSHA, however, is enforceable, and OSHA does quote NFPA 70E often, so it's not directly enforceable, but you can see inspectors and so forth force it through OSHA.
Okay, Ken, I'm going to ask a follow-up question here. Is arc flash labeling a mandatory requirement per OSHA and NEC?
Yeah, so both NEC and OSHA do require, some form of calculation to determine what incident energy level or what protection is needed to work on the equipment, and they do have a requirement for labeling.
Okay, thank you. Zia, this next question is for you. What information is necessary to calculate an arc flash rating? How do you tell if software is outputting the correct arc flash information?
Again, another good question, and the challenging is at least the second part, the answer to the second part. But let's just start with the first part. I think during our presentation, we mentioned the factor, the parameters that needs to be important to perform the arc flash instant energy calculation, minimum and maximum short circuit injecting to facility, voltage variation, the type of equipment, the type of is it switch gear, MCC. Really, that is really important, because defining the type of gear, either it can be panel, switch gear, or MCC, or cable, is really impact on the short circuit, on the arc flash study. Therefore, I highly recommend make sure the type of equipment that you are study, define that, not just call it anything that you want to. The enclosure size, working distance, electrode configuration, is it horizontal, is it vertical? Those are the parameters that will go to a study, and you saw that on C area plot, that concept was discussed. Anyway, that's part of the first part. Second part, how do we know the software will calculate correctly? We have several industry software, and it's been around for many years, and we all use it. There is not really something that we able to say, okay, this software is the one that mainly in industry practice I'm referring to. SKM, ETAP, Easy Power, those are the major one. Those are they've been verified and checked, and we've been practicing, we've been using it. Well, what we can do as a user of any software, if we see an issue or some type of that is really obvious, our obligation is to report to the software company and providing the feedback from us that would help. Some company like ETAP, they do have a QA program, means qualified the verification, and they doing the checking the calculation. Therefore, at this point, we just take the result as is. If you see any with the major software industry, but if you see any problem, we have to notify the company.
Great.
That's my take on that.
Thanks, Zia. All right, Ken, I'm going to send this next question over to you. If you're looking at IEEE 1584, what nominal voltage level is required for equipment labeling? So we're talking about 208 volt. I mean, can you go into a little bit of detail about that?
Yeah, so the way that code reads is under 150 kVA transformer on the 208 side, the magnitude of the current, the inlet current of that transformer is low enough that it doesn't require arc flash study, or I guess I still think, you know, it's a good idea to have a label on it, but it's not required by code as far as a PPE. They feel that it's, you know, the study's been done, that the magnitude of the current at that point is low enough that the injury is not as severe, so it's not required. But anything above that is, you know, the labeling is required, and then anything above the 1200 amps requires not only labeling but some type of mitigation.
Excellent, thank you. Zia, the next question is for you. Do the other software modeling programs, so we're talking about SKM, Easy Power, do they do that C-plot analysis?
No, the answer is no. Again, as I pointed out in my presentation, the C area plot is the concept, is a new concept. It's been around probably less than a year or so, and is performed and done by ETAP at this point. And not Easy Power and SKM or any other, at least I don't know, but most likely not.
All right, thank you. Let's see here, Ken, I've got lots of questions for you. Here's the next one. How does arc flash mitigation for DC systems compare to that of AC systems?
So that's an excellent question. So, I mean, the short answer is there is a lot more arc flash mitigation on the AC system than the DC system. The nature of the fault, the zero crossing on the AC system just lends itself to a lot more mitigation techniques. On the DC side, you know, I agree. I see some of these questions, you know, between the, you know, solar arrays, fuel cells, batteries, all that type of systems are all on the DC side. So there is more and more DC systems that need to be studied. And the programs like SKM, ETAP will do a DC fault analysis for arc flash. So it is very important to do that. Unfortunately, right now, I don't think there's a lot on the DC side as far as mitigation, you know, the breakers and settings and so forth. You really want to look at minimizing the size of the DC component, if it's a battery system, inverter systems, to minimize the amount of current that can flow into the fault, to kind of mitigate that, the amount of flow or the magnitude of the fault. You know, the short answer is DC systems do need to be looked at. They do need to be included in the fault current study. Once you find out, trying to mitigate it down is not as easy as it is on the AC side.
Right. Okay, good. Thank you. All right, Zia, this one looks pretty complex here. So I'll read it and I can go back to anything. Some of the software modeling tools, such as SKM, may not model the reduced clearing time from current limiting fuses. How do you model and calculate arc flash incident energy levels if the software model does not provide those calculations?
Good question, and is this been going on, and people need to actually using those type of equipment fuses. Just going back to answer to this question, some software such as ETAP, they have their a few approaches to deal with the current limiting fuse. Some software they may not have, as our friend pointed out, like SKM or other. Again, this is my recommendation or my suggestion. Sometimes in the software that we don't have those capability, we have to get around it, meaning that create some cases that we're able to achieve our objective. Maybe one way that we can deal with this situation, because the current limiting fuse, as we know, minimizing or limit the fault current through the fuse. Therefore, if we're able to understand or how much current will be passing through based on the limited number, what we can do, we probably can injecting a source, a current source, to represent that amount at the location that we are trying to study, and study from that point. Therefore, two steps. Just one required to look into the kind of how much current will be passed, and then the second step, going back to the model and put that amount of the current in terms of the if you will, short circuit or a power grid or power utility injection to the system, that maybe we're able to get around this problem.
Okay, interesting. Thank you. Okay, Ken, this is kind of a specific question. Are infrared windows available on arc-resistant switchgear?
So the answer is yes. That picture I showed in the presentation was actually infrared glasses on the back of arc-resistant switchgear. The glass is I want to say it's almost like a bulletproof glass. It's very strong a glass, and you can see that the encasing of the glass is welded to the frame. So it is available. It just has to be beefed up to handle that with, again, handle that explosion and maintain it within the gear.
All right, let's see here. We've got more questions. If you do have questions, you may type it into the Ask a Questions box on your screen, but we won't get to everything today, so we will answer them online as well. And you'll receive information about this webcast event as an on-demand event and about that additional information. All right, Zia, another question for you. Is selective coordination only required on 480-volt systems?
The answer is no. That required for any system. Regarding from the downstream device or voltage level, it can be 120, 240, all the way to utility side, which is the medium voltage system. Because the selectivity, that means reliability of system operation, meaning that if there is a fault on downstream, that doesn't matter. We don't want to have a malfunctioning of the relay or protected device circuit breaker that's not supposed to be action during that. Therefore, at any voltage level in the facility, because of the reliability and operation, better reliability, we need to have the coordination study. This can be done from the bottom up or from the up down, and to make sure all the voltage level, it can be 4 kV, 13 kV and higher, are coordinated, because mainly we don't want to lose one portion of this entire system because there is a fault on one small system.
Yeah, I think the other thing we have to talk about, I think he might have been asking about selective specific, where you can't have any overlap specifically in like the instantaneous region. I agree with you. The coordination pieces so that we don't have that propagating fault. But from a selective, like you see on emergency systems where they specifically say you can't have overlap, and a lot of times it's up to a certain amount of seconds, so it doesn't account for that overlapping part in the instantaneous region. But again, it is dependent. It's not just dependent on 480. So I agree with you. It's not.
Yeah, but I'm going back on Ken on your point. Definitely, we actually downstream device. We always say we always see that overlapping, because one of the main reasons that downstream devices we typically using molded case circuit breaker, which do not have the adjustable settings. Therefore, if the question in that views, therefore the answer would be we have seen in many industry a facility overlapping in the region of an instantaneous region, because one of the main reasons that the downstream we are using molded case circuit breaker, there is no settings, there is no adjustment, we cannot do nothing about it, and we just have to, in most of the case, we live with it, unless there is a kind of, we're changing everything. If you want to do more action, in most cases that are critical, we need to move from the molded case circuit breaker, for example, to more adjustable power circuit breaker and utilizing that.
Yeah, and I agree. And a lot of times in that situation, like the NEC 708, the critical operations power system requires selective coordination, no overlap. In a lot of cases, then you'll go to the fuse where it's the instantaneous is shorter, and you can now, coordinate them well without having them overlap. So, yep, I agree.
All right, that's tons of detailed information. Thank you so very much. So unfortunately, we don't have any more time for questions. So I'd like to thank you, Zia Salami and Ken Kutsmita, for those extraordinary answers and for some really great information in that presentation. Thank you so much for sharing your knowledge about arc flash mitigation. I'd also like to thank ABB, ASCO Power Technologies, and Meltrick for supporting this education session. Before we go, we do need some feedback to improve future webcasts and education sessions. A short survey will pop up on your screen as soon as this webcast ends. Please take a few moments to complete it. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, thank you for joining us, and we'll see you again at the next education session. Goodbye.
Thank you.